Hey folks, today we are going to start the second unit in AP Physics, which is kinematics or motion in two dimensions. So in the previous unit we did kinematics in one dimension. Either something was moving left and right along the ground like a car, or something was moving up and down like a ball falling or throwing a ball straight up into the air. So now we're going to talk about two dimensions, and in order to do that, we need to know about vectors. And again, this is primarily review from your previous year and also your previous math classes. However, I think it's good to review, and I do have a question at the end that's a little different than probably something you've done before. So let's start with numbers can be, or values can be categorized in two ways. We have vectors, and we have scalars. Okay, and I'll start with scalars. Scalars are simply a number with units. So examples of scalars would be like money. So you have $20. 20 is a number or magnitude, and dollars is a unit. Um, a height would be a scalar. You are 5 feet 9 inches tall. Okay, so feet and inches um, are the 5 and the 9 are the numbers, the magnitudes, and the feet and inches are the units. Okay, vectors have a number or magnitude. They have units, but they have one more thing, and this is the most important thing for vectors. They have direction. Oops, and I need to spell that right. That's the most important thing about vectors. They have a direction. Okay. So let me give you a couple examples that have to do with physics. In physics, a scalar would be distance, d, how far you drove. You drove 50 miles. Okay. In physics, we have displacement, which is delta x. And that's a vector, so we put a little arrow over it. So how would that look different than distance? Well, you would say I drove 50 miles west, or I drove 50 miles 24 degrees north of west. Okay, so that has, not only does it have a magnitude and a unit, it also has a direction. Similarly, for a scalar, you have a speed. I'm driving at 30 miles per hour. In physics, it's a velocity, is a vector. I'm driving 30 miles per hour north. Okay. Also in physics, acceleration is basically always a vector for us. We're accelerating to the right, to the left, up, down, etc. Okay. Now, there are a couple different ways to represent vectors. Okay. One way you might remember is writing a magnitude, which I'll abbreviate with that, and a direction. So for instance, let's say I drew a vector, it looks like this, and let's say it's a displacement vector. Let's say it's 10 meters. We'll call it vector A. And let's say the angle with the vertical that I've drawn here is 30 degrees. Okay. So how would you write that as a magnitude and direction? Well, it turns out there's a couple ways to do that. You would say vector A, okay, is 10 meters. You write a little at sign, the ampersand sign, that gives a direction, says at. One way to write this would be 30 degrees west of north. Now, let me be really careful with this. West of north. Okay. So what that means is you start with the of part. Okay. So you would say I point due north, and then I rotate 30 degrees west of it. Okay. So imagine you're standing in the front yard. You would grab a compass. You would point it north first, and then you would rotate counterclockwise or left 30 degrees and point that way, and that would be your direction. So west of north, when it says of north, you start on that first. You start north and then rotate of it. Okay. There's a couple other ways to write this. You could write 60 degrees north of west, which means you would start by pointing west down there, and you would rotate 60 degrees clockwise or north. And that would be the same direction. So those two are equivalent. So if I wrote 30 degrees west of north and 60 degrees north of west, that's the same answer. A few of you may write 120 degrees. Now, what does that mean? That means that if we call, our coordinate system never eat soggy waffles, north, east, south, and west. Some people say east is 0 degrees, and if you rotate 120 degrees counterclockwise from there, that would be our same direction, okay? I prefer not to use that because if you're in the military, north is 0, in which case 120 degrees would be down here somewhere. So if you just say 120 degrees, it's not really accurate. Now, you could say 120 degrees counterclockwise, so we call that CCW, from east. Okay, now that would be acceptable. Everybody would agree on that. But if you just say an angle, just 120 degrees, then it's a little confusing. It depends which coordinate system you're using. So that's representing vector A as a magnitude and direction. Another way you can represent vector A is with components. Okay, so if I redraw this triangle, that's 10, and I'll draw this and this, okay? So the horizontal one, we can call that AX, and the vertical one, we can call that AY, and this angle here is 30 degrees. AX would be, that's the opposite leg, so it'd be sine, so it'd be 10 sine 30, it would be 5. And AY would be 10 cosine 30, which would be, if you write that in calculator, it's approximately 8.7, okay? Now, here's how you would write this in unit vector notation. So you would say vector A equals, now this may be a little new for a few of you. We don't write AX and AY. We write I, J, and K components, okay? So X is like I. So you would say, and that goes, this AX is to the left, so that's the negative. So you would say negative 5 I hat. And you literally pronounce that I hat. It's like an I with a little hat over it, okay? So that means negative 5 in the X direction, or 5 west. And then we go up 8.7, so plus 8.7, and that would be J hat, okay? Later on, we'll have 3-dimensional vectors. Well, you'll also have a K hat direction, okay? So like imagine you got north, south, east, and west, and then you have up and down. Well, up and down, that'd be your K hat direction, okay? And then you would have a unit on this, would say meters, okay? So that's how you write a vector in unit vector notation, okay? It's just a very convenient, quick way to write vectors out, okay? Now, let's say we had vector A there, and let's say we have a vector B. I'll just draw vector B over here on the right. Let's say B is 15 meters, and it's directly to the right, okay? I might ask you to add A and B together, okay? So if I ask you to add vector A plus vector B, well, there's a couple things we may ask you to do. First, we may ask you to graphically add it, okay? So graphically adding it means simply drawing it out. So if I do A, I'll start with a dot, and A goes like that, and it's about 10 long. And then if I add B, and I'm going to add these tip to tail. So at the tip of A, I'm going to start the tail of B, and B would go that way. And this would be A, and this would be B. The result, we started here, and we ended there. So my result looks like that, and it would be A plus B. It started down there at the bottom, and it ends there at the top. So that would be A plus B, okay? Now, that's graphically adding, and then we're just getting a rough sketch of what it's going to look like. To actually add A plus B and get an actual numeric number out of that, what I would do is write A, which we know is negative 5 I hat plus 8.7 J hat, and write B. Now B goes 15 to the right, so that's 15 I hat, and it does not go up or down at all, so this would be 0 J hat. And then you just add the components. So A plus B would be 10 I hat plus 8.7 J hat. And if you were to add those two components together, so 10 I hat would be to the right and 8.7 would be up, this is A plus B. This line and this line are the same thing, it's just in a different kind of triangle. But now you have a right triangle. You could easily find the magnitude of A plus B. You would just Pythag 10 and 8.7. And then you could also find this angle by doing inverse tangent of 8.7 over 10. inverse cosine of 10 over whatever the hypotenuse is, or inverse sine of 8.7 over whatever the hypotenuse is, and that would give you the magnitude and direction of vectors a plus b. Okay. Now, what if you were subtracting? Oh, first of all, before I do that, does it matter if we do a plus b or b plus a? Well, over here it sure wouldn't matter, right? If you put b and a, if you swap spots and add them, you're going to get the same thing. If you look at it graphically, if we start here and draw b first and then draw a, well, look, we still get an arrow that points up and to the right. This and this are the same, okay? So it doesn't matter what order you add vectors in, just like it doesn't matter what order you add numbers in, okay? Now, what about subtracting? What if I wanted to do a minus b, okay? Well, graphically speaking, you would draw a first, okay? So here's a. And then for minus b, all you would do is have it go the other way. So this would be minus b. And your result would start here and end there. This would be a minus b. Okay. Now, and it wouldn't matter. And now, would it matter if you did b minus a? Well, that would matter. You would get the same triangle, but it would be pointing the other way. If I did b minus a, okay, so b goes to the right, and negative a goes this way. Okay, so this would be b minus a. You would get the same length there. This would be b minus a, but it points the opposite direction. So a minus b and b minus a would have the same size, but they'd be the exact opposite direction to each other. Okay. Now, a couple other notes. When you're doing something like this, okay, you got a not right triangle, you are totally welcome to use any shortcuts that you know to add those together if they ask you, for instance, for a magnitude of a minus b. So, for instance, you can use the law of cosines, which is a squared equals b squared plus c squared minus 2bc cosine of angle A. So if you know two of the three sides and an angle in the triangle, you can use this to find the third side, okay? Or if you know all three sides, you can use this to find one of the angles. You also can use the law of sines, which is side A over sine of angle A equals side B over sine of angle B equals side C over sine of angle C. So for instance, in this triangle up here, if you call this side A, the angle opposite would be angle A. Okay, so you can use the law of sines for that. So you're welcome to use these two things. You've learned them already in trig and pre-calculus. But if you want to use them for any of these, you're certainly welcome to. All right, I do have one more short video after this doing an example with vectors that I highly suggest that you watch. Have a good one.